So I'm going to go ahead and get started with class today. So the first question that we have is, I want to make sure that you guys know how molar mass is related to all these colligative properties. Did anyone do this problem after class? It was in the slides that I uploaded, but there was no solution posted on it. Anyone do it? Okay. So I'm going to give you guys about 2 minutes to think about how to set up this problem. Try to figure out how to approach it. Focus less on crunching numbers, focus more on talking to the people in your groups that you're sitting next to, how we would solve this kind of a problem. Yeah, can you guys like spread out so that we can actually get to you guys, so move that way. Welcome Thomas as he comes with a big movement. It's like half the classes. I mean, they should come with you, right?
Yeah.
How you doing? You got my email? So Friday night, scratch off.
And I can't remember what time I usually schedule my TV.
Whenever on the same day is fine by me. So whatever works. You sent an email today? Yeah, I didn't have any notification yet, so I thought I might promise you to. Almost. 0.0821.
6. ATM.
Okay, units are incredibly important because if you have a different set of units, it's a totally different number. What are your units here? Your units here. Three of you guys probably move up into the space. Come dance with us.
Whatever spits out, we know how many leaders we have. What are you
All right, let's do this. Is anyone, can I have 3 volunteers to write up your group's work on the wall? As you don't have to be done. Morgan, go for it. All right, Valerie and Sarah, you guys go up and write it on some space, so you guys can write here. Another group or 2. I mean, as many people as 1, but I want at least 3. Sure, go ahead and write up your work, please. And if anyone wants to, there's still more pens, so write it big enough so people can see when we're going to talk through it. Don, can I get you to roll over here and join Michelle? Please. Thank you. Michelle, do you mind turning around and joining with Don? You guys are like...
my clicker.
Is it just because whenever I come, you guys just throw stuff on the floor?
No, this is in my mind.
As long as there's not a computer, I think we're better off. I guess the most important part of it.
Yeah, I have it down.
How'd you guys do?
So, I don't know if I got the right answer, but that's the molecular mass that I got. But, I'm really bad at significant figures, so with this answer, I don't know how this is just figure price.
So what you got here is measured, convert this to liters, that way you see that your liters goes away. So right now you're trying to find it.
I just like this problem with this on Saturday. And I don't understand polarity of grams
So what about this?
per liter. So then multiply. I don't understand why you need 5 multiply by
All of those you have to say which one.
I don't understand why you do that.
So would it be
No,
this one? The 25 though.
So when you convert to Kelvin, it's 98, 96, 57. So think about how you added those two together, how you got this number. Think about the process. This is subtraction of different sig figures. So there's a chemical one. So you can go look at the chemicals. There's one on sig figs. It does a really nice job of highlighting the subtraction versus so this would be 3 sig figs based on additional numbers. Wait for the decimal so that is it versus that. Because they're all
and divide the number of grams by the number of kilos.
How you doing, man?
Not too bad, are you?
All right. You want to scoot in and join so people are going through it?
Sure.
How about? So what do you need to pass in order to get rid of the molarity? It's one of the steps along the way. But
The moles of the protein, and you need how many grams and
so you need the ratio of grams. You have the two of those. All right, let's do one more minute for those writing on the wall. Try to get everything up there. For those of you working in your groups, make sure you clearly explain the path you went through. And then you can multiply it by
And then after, how many are we in?
And now that you have your grams, you have the grams. And you have to convert your to like relative grams. So I do like times divided by or number and then the number that you get will be grams per mole. So it's 5,000.
Yeah, that's why I put it in because I noticed that it has letters.
Yeah, the chemistry was too
I just have to scroll all the way through. Oh, it's so good. It really doesn't vary. You get 5. Yep. Yeah.
All right, guys. We have a lot of things written up here. What was the most common place that people messed up or got sloppy? Units. Okay, so if you're using, Morgan didn't like hers, I guess.
Oh no, I got this. You got it.
Okay. So if you pay really close attention to your units, this kind of a problem becomes much more clear and dry cut. So what's the big approach? Can someone say high level? How did you use all the information that we were given in order to figure out what the molar mass of this protein was? You convert? Okay, you want to explain, Shane? So your work's put in here in orange? You want to explain? Okay, so let's see if anyone else is willing to explain. Big picture, what are we trying to do? So conversion is part of it? Nia? Okay, so we have an osmotic pressure formula, which is, did anyone write it up on the wall? Without stuff filled in? No. Okay, so pi equals I times molarity times the gas constant times temperature. All right, and then if we have that, then how do we use it? What do we do with it? Go ahead, Mia.
Because that will give you the moles, and then
So careful when you're saying that. So we solve for m, and first of all, I'm going to give this guy over here a hard time because there's a little m.
That was a big M in my book.
Okay, well, maybe you scared it into looking like a little m, but it looked like a little m. So we can solve for molarity because we have, what do we know? Everything else. Fair enough, okay? We know we have osmotic pressure. We know that we have the temperature 25 degrees Celsius, right? We can't use Celsius because that gas constant has Kelvin. If we don't write out the units, we might accidentally put in Celsius. Okay, do we know the Van Hoff factor? If it's a protein, we assume it's 1, because it doesn't dissociate to any ions. And then our gas constant. Is there only one gas constant? What's different between different gas constants we can find? Katie? Great, so there's a ton of different units, and we'll derive the gas constant today. We're going to start in gas laws. So I want to make sure that whatever gas constant you use, always write out the units, because it might have torr, it might have atmosphere, it might have bar. There's a ton of different ways of measuring pressure. So that's really important. So then, as all 3 different people that wrote it up showed, the only thing that we don't know is molarity. So we can solve for molarity. And what I want to see you guys write out would be specifically, so you have it over there, and you kind of have it, moles of protein per 1 liter of solution. That's what we can find. So then how do we go from molarity, from moles of solute or protein, to liters of solution? Then how do we actually find the molar mass? What are we looking for? What are we trying to find, Alex?
I'm trying to find the ratio of grams of the solute to moles of the solute.
Great. So we know that molar mass, molecular weight, is always going to be a ratio between the grams of, in this case, it's the protein, to moles of that protein. If we can find the grams and we know the moles, we know the molar mass. That ratio is always going to be constant for that particular protein. Do we know one of those by chance already? We know the moles, right? No. Let's look up here. We dissolve 447 milligrams of an unknown protein. So 0.477 grams. So the only thing we need to find is, if we find the moles in this particular solution, we know the molar mass. Is that what you guys did? So how do we find the moles? Alex?
Well, I have a question because I didn't round anything until like the end, so my answer came out like different than theirs.
Great, so you should never round until the very end. So that might have been, depends on how, do you use 0.0821?
8.54 times 10 to the negative 5th. I got 8.53 times 10 to the negative 5th.
Up there, I put the rounded number, but on the calculator I didn't have.
Yeah, so what you want to do, and I always recommend, if you have a graphing calculator, always use your graphing calculator. You guys know how to store your numbers in your graphing calculator? If you're not comfortable with it, if you end up with an answer, there's a little button that says STO with an arrow next to it. Hit that, and then select 11. So you can store a particular answer as A. and then next time you type in alpha A, then it is that number stored as A, so you don't have to run anything. You include everything in all calculations. If you want to see how to do that for class, let me know. So, the non-rounded answer that we found for molarity, how do we go from the non-rounded answer of molarity to finding the number of moles of that solution? Val?
We multiply by the liters of solution that we had in the problem.
Why? Why do you multiply molarity times liters?
Because liters is in the denominator, and we want to cancel that out to just get moles.
Okay, so mathematically we can cancel out units, unit conversion, as Shane was saying, we can find the number of moles. Can anyone say it another way? How do we use molarity to find the number of moles if we know the volume? Michelle?
You divide the molarity by the amount of liters you have.
Why?
Because
What is molarity?
it's moles per liter of solution. So if you have a liter of the solution, you're going to have that many moles. We have less than a liter, so we just divide it by that.
Great. So I love that you're saying if we had 1 liter of solution, we would know we have this many moles. We don't. Right? We have less. But that ratio always holds true. The concentration is always the ratio between solute and solution for molarity. So we can always back it down and we can say, well, if I have less than this, I'm going to have the same proportion less here. So the proportionality is what we can use conversion factor. So molarity is in essence a conversion factor where we can actually do, where's space? We know that if we have 0.00500 liters of solution, and we know that the concentration is that we have, what's the number? 1 point, times 10 to the negative second. Is that right? Moles of solute for every 1 liter of solution. So this is one way to use it as a conversion factor. So for every 1 liter of solution, that is the same as this many moles of solute. So if we have this much, we can use it as a conversion factor, we can find the number of moles of solute. Okay, so we find the number of moles of solute, then what do? Megan, what do we do once we have the number of moles of solute? Percy.
We can figure out the molar mass
How do we figure out the molar mass now?
using the 147 milligrams and everything that we just calculated.
Okay, so how do we compare those two? Why do those two help us find the molar mass? Okay, I'd tweak that a little bit and I'd say it's the ratio between the weight and how many moles. So the molar mass, how many moles to how much mass. Okay? So based off of that, let's see what you guys, has everyone clicked in your answer? We have fairly close numbers. So what's the big difference between most of these? So how do we determine how many significant figures this answer should have, Jose?
The weakest link in the problem.
What's the weakest link?
Any of the ones with 3
Okay, so any. So before we dig into each specific one, are we going to use the gas constant to limit our sig figs? No, that's a precise number. We could go look up a much more precise version of that. So we're going to use any number that had someone's measurement and imprecision built into that measurement. Did someone measure the mass of the protein? Yes. Did someone measure the volume? They were able to say, well, it's accurate up to 3 sig figs. Did someone measure the pressure? The machine did. What about temperature? So the first thought is it's 2 sig figs because it only shows 2 sig figs, but there's 2 separate rules, remember, for sig figs. If you're adding and subtracting, 25 degrees Celsius plus 273.15 Kelvin is 0 Celsius. So what limits our number of sig figs there?
There's no decimals on the 25.
The fact that there's no number past the decimal on 25. It's always relative to the decimal. So this is 298 Kelvin. That is the accurate temperature that we can use. How many sig figs is that now that we multiply that to our gas constant and everything else? 3 sig figs. All right, so you got to think through every single calculation. What's the weakest link in this calculation, this calculation, this calculation? The rules are different for addition, subtraction versus multiplication and division. So if you're not comfortable with that, that Chem tour would really help with that. Don't lose points on the exam for this. It's really silly.
People forgot to put the units as well when it was alcohol, benefit, numerical.
Did anyone notice to actually do that besides Jake? So if you were to answer on the exam, the molar mass of the protein is 5230, you would lose points. Did anyone actually click in one answer down here? Someone put grams.
Hey, there I am.
Is there another way that we could have entered this?
Big M.
Big M is moles per liter, so probably not. Wait, before we get there. How could we have answered this? Was anybody here in class on Thursday? What was another way we said grams per mole? Dalton. So 5.23 times 10 to the third Daltons would have been fine. 5.23, oops, 3 is better. Kilodalton would have been great. That would have been the best answer. Kilo means times 10 to the third. Daltons means grams per mole. When we're talking about proteins, Daltons are used much more frequently than grams per mole. If you did it in grams per mole, it would have been okay as well. The clickers are kind of hard to do that. Don, question?
I just had a quicker question, because I put in 5.3, but I don't know how to put in units or EE, anything else.
So there is E in any of the numeric stuff. So you can do E, which means times 10 to the, and then you do E3. Or there's a little caret, and you could do 10 caret. So when alphanumeric, it's maybe not as easy to see. All right, any more questions? You guys ready to do this on the exam? Okay, well, you got until Friday, so you're good. All right, so what I wanted to show is there's another way we can look at this as well. I like that everyone worked through their own way. We found what we don't know. We used how molarity relates to molar mass in order to find moles. And you guys as a comparison. So what you're I'm going to show you really quick as well, is that for any of these colligative properties, we can find molar mass. So you guys, I'm sure, are comfortable with this relationship, that the change in freezing point is related to the Van Hoff factor times freezing point constant times molality. What are the units of molality? Claudia? Moles of solute per kilogram of solvent. Great. But what we just found a minute ago here, and how you guys have used this frequently, is that if we know the mass of the solute, we're going to start to unpack some units that are kind of hidden within moles of solute. That moles of solute is really how much mass you dissolved times, or divided by the molar mass, really. So think about the units. Molar mass is grams per mole. If you do grams times grams per mole, you find the moles. Everyone following along so far what I'm doing? So this is hidden in the top of the moles of solute, which is hidden within molality, which is part of our equation. So if we wanted to, we could rearrange this whole equation, and we could plug in, instead of moles of solute, we could have this relationship here, which is grams divided by molar mass. Grams divided by molar mass, or molecular weight. You don't like this, Don? So this is a way to just think about how the units relate to each other. You guys can go through this kind of calculation if you want. I want you guys to write out, if we rearrange this equation to solve for molecular weight, what is this equation, so we can take out where I have my hand, right? So change in freezing point is equal to this. I want you to rearrange this equation to solve for molecular weight. You have space on your paper for that, I think. Is that true? Yeah, it's kind of in question 2. So rearrange that equation for molecular weight is equal to a whole bunch of stuff. Brianna, are you not happy with this?
No, I'm not.
Do you know the question, what I'm asking?
Yeah, I know what you're asking, but I don't really understand what's up there right now. Like, I don't really understand what I'm looking at.
So we took molality, which is this.
I get that part, I just don't get, like, once you rearranged it and added in grams over molecular weight, like, why is grams over molecular weight the same grams over moles?
So the grams times 1 mole over grams, that same thing as grams divided by molar mass.
Okay.
So the thing that's in the red circle is the thing that's in the red circle. Is the thing that's in the red circle. All those are equal. So it's on the bottom. The whole thing on the bottom. You don't like this rearrangement?
No, it's like making, like, I just understood how everything connected, and now it's like,
Use the other way if you want. All right, so let's bring everyone back together. So mathematically, what do we do in order to get molecular weight isolated from that equation? Chelsea? Okay, so we could move a whole bunch of stuff to that side of the equation. Did anyone do another way? Morgan? Anyone do a really simple way? What's that, Shane? Multiply both sides by molecular weight. So if we multiply both sides by molecular weight, here's the two sides. The right side, molecular weight goes away, and it's on the left side. So what we're basically doing is we're multiplying both sides here by molecular weight, and then dividing both sides by delta TF. Oh, that M should not be, that should be grams, sorry. Sorry, grams. Typo. Okay. So if this makes you very uncomfortable rearranging mathematical expressions in order to bring out molar mass, then you can go about it the way we did earlier. What if we have osmotic pressure? We have osmotic pressure is molarity times I times R times T. Molarity is moles of solute per volume of solution. Once again, we could do the same rearrangement if you guys wanted to, and you would have this kind of a relationship. So I'm just trying to give you guys different options of ways to rearrange mathematical expressions in order to solve for unknowns. Is this valuable to anybody in here? Okay, so a couple of people like this. Most people don't like it too much. All right. So keep in mind that osmotic pressure is actually used in a lot of biological labs. There's a thing called a nanodrop that actually uses this in order to determine what the molar mass of your protein is and what the concentration of it is. We usually don't use osmotic pressure for non-electrolytes. What's an electrolyte? Miata? What's an electrolyte? It disassociates in solution. So give me an example of an electrolyte and a non-electrolyte. Great. Sodium chloride is a great example. Fantastic. Very good examples, Miata. Okay, so electrolyte, non-electrolyte, those are the terms we use for a lot of this. All right, you guys want to do another one? No, I'm not going to do another one. All right, we're going to shift gears. Now we're going to get into working on applied gas laws. Read through this question, see which you believe stays unchanged when you warm a sample up that is in an enclosed container. You guys are not in agreement. Talk to your neighbors. All right, so who wants to share with the class? Salma? Okay, so we might even almost say that because of increased collision frequency, that's what we measure as higher pressure. Great. Okay, and what about the other two? It will or will not? Okay, so why would the average kinetic energy change? So anyone want to add to that? Thomas? Okay, so this is true for what state of matter when they do this? Okay, this is gas. So what are they going to be doing? Okay, so kinetic energy means they're going to be moving around way faster, right? That's what happens when we heat up gas molecules. They move around much quicker. So that leaves us with the process of elimination as density. Is anyone comfortable explaining why density remains unchanged in these containers when we heat it up?
Because density is mass and volume, and if you're just...
It's what?
Wait.
It's not mass and volume. It's the ratio of mass to volume in it. So in a given mass space, how much mass there is.
So when you heat it up, those variables don't change. They're constant. So density is not going to change.
So where is all the mass in our sample?
In the steel container.
So we're not talking about the steel. We're talking about the gas within it. Where is the mass in that gas sample? In what, Don? In the nuclei of all of the individual atoms, in the molecules, depends on what gas it is, right, if it's molecular or not. So the number of nuclei in that given space don't change, or the number of nucleons, the protons and neutrons, even if we heat it up so much that we bust apart some of these atoms, and we do nuclear fusion or nuclear fission, which can happen at extreme temperatures like in the sun, that's not going to change the number of nucleons, so those are going to stay constant. Val?
But density changes when phases change, right?
Density changes when phases change if they occupy a different volume. So if there's no constraint, so like if we boil some water in the room, then that volume will change because it's not constrained. But if we had it in a closed steel container and we heat up liquid water, if you think back to your phase diagrams with all the different pressures and temperatures and what phase we're likely to find it, we'd have to use that to figure out what temperature would need to be overcome within pressure in order to figure that out. So it's going to be a bit more complicated. So I agree with the majority of you guys. So the goal for today's class is we're going to be thinking about gases from a molecular level, and we're going to do some mathematical relationships within that. Your homework that's due this weekend has gas laws in it. Not as much calculation as there is theoretical. Our focus is really theoretical, and you need to be able to use relationships as well.
Is that on the exam?
So some of gas laws, everything from today is fair game for the exam. What we're doing on Thursday should support what we're doing today in class, so it'll only reinforce. But if there's something that we touch on for the first time on Thursday, that will not be on the exam.
So do the homework that's due Sunday.
It's up there.
So like that homework is going to be covered on the exam?
Parts of that homework will be covered on the exam. So after class today, I would look through what's on the homework, I guess, and see what's relevant to today's course material versus for Thursdays. And that. So let's get through some of the stuff today, and then you can post a question on Canvas discussions afterwards, and we can kind of parse out the details there. Fair enough? So I want you guys to derive the gas constant you guys have been using. So to start with, we're going to say that the gas constant that you've been using is at standard temperature and pressure. What's standard temperature, Brianna?
0 degrees Celsius.
0 degrees Celsius. And Michelle, what's standard pressure?
Is that R, like in the other equations we've been doing?
So we're going to derive R, but in order to do that, we're going to do it at one particular set of conditions. So what is standard pressure? We say standard temperature and pressure, it's 0 degrees Celsius and?
0,
No. 1 ATM. Okay. So I love it, Michelle, when you look at me when we're talking in class, but I also do put up some cheat sheets for you guys. Okay, so that's our definition of standard temperature and pressure. 0 degrees Celsius, which is how many Kelvin? 273.15 Kelvin. All right, and then the other factor that you guys are going to need to know is that at standard temperature and pressure, this is kind of mind-boggling, by the way. You guys maybe already know the statistic. Any gas, doesn't matter what it is, if it is in gas form at standard temperature and pressure, what volume does it take up? 22.414 liters. And there's a flash that shows about 22.4 liters. Bigger than a basketball. That's how much volume it occupies if it's 1 mole of gas. Why is that crazy? What's challenging about that statement to us? Different atoms are different sizes, different molecules are different sizes. It's a lot of volume, right? Think about, so let's say if that's water. So let's just say, for argument's sake, if we had a mole of water in gas form, it occupies more than a basketball, almost double a basketball's volume, right? How much volume does 1 mole of water occupy when it's not a gas, when it's a liquid? Talk amongst your group. How much volume does 1 mole of water occupy in liquid form? One what? Oh yeah, sorry.
How many
1 mole of water.
would it take out?
So Demetrius, watch yourself. 1 mole of water, how much volume does it occupy?
Is it the same thing?
If it's a gas, yeah, but we're talking about as a liquid. What do the molecules of water look like as a gas compared to liquid? Show me with your hands. Okay, what is that?
That's liquid.
Okay, in gas? Great. Okay, so they're much further apart as a gas than they are liquid. So how much volume does liquid water take up if we have 1 mole of it? Who was able to answer that? Alex? Can you at least tell me how much it weighs? 18.01 grams, okay? So if we know how much it weighs, can you tell me how much volume it takes up? Is there a relationship between those two? Okay, so what's the density of normal water? Justin?
So
1
gram per
1 gram is the same as 1 milliliter. So if we have 18 grams, we have 18 milliliters. Okay, 18 milliliters versus 22.4 liters. What's the difference in volume between those two? It's 1,000 times more volume that it takes up. So I agree with you, Taylor. It's a lot of volume. Okay, and that doesn't matter what the molecule size is, what the atoms are within that. If it is at room temperature, at standard temperature and pressure, if it is in a gas form, We know liquid water's not, so that was kind of limitation of my analogy there. But if it is, it's 1,000 times more volume that each molecule takes up. Okay, so I want you guys to use all of the numbers that we just talked about. You guys know this equation, right? P equals nRT, ideal gas law. I want you to use that to solve for R at standard temperature and pressure for 1 mole of substance. Take 1 minute. You have all the values, plug all the values in, solve for R. What is R? And focus on units. So guys, what are we using for a number of moles? 1. What are we using for our temperature and pressure? Standard temperature and pressure. Okay, so use those to solve for a numeric value of R. And put the units in once you solve for it, please. Not a question. All right, so, Mommy, what'd you find? Okay, so you derived the gas constant. So then, Morgan's question is a good one.
What purpose does the gas constant serve? Like, who decided that needed to be there? Why can't it just be PV? It was NT. What does R serve?
Anyone have a good answer? Say again?
So you can change your variables. Like we've been looking for pressure before, so P equals nRT over B. So without that constant, you'd never be able to find out what your atmospheric pressure was.
So what the equation, are you what caused me to answer that?
Well, I was going to say, like, you basically answered that because you standardized everything else, what would basically be 0.
So what we're doing is we're taking all of these variables and we say that we know that somehow pressure and volume are related and they're inversely related. And through the gas constant in this expression, we can predict, if we have a number of moles of temperature, we can predict how changes in one will affect the other. And so it's a scaling factor, if you will. That if we use this set of units, the scaling factor is 0.08 to 0.6. If we use another set of units, are we going to have the same R? What if we're using torr? What would be different about our calculation? So 1 atmosphere is 760 torr, so we would use 760 torr for our pressure, and then those units for R would have torr in them, and it would be 760 times higher. We could do this for any different set of units that we want, and we'd still have that same relationship, that same scalability, but it would just depend on the units that we're using. So whenever I see R, whenever you guys use R, absolutely include your units, please. All right, so for the rest of class today, we're going to talk about where pressure originates, and I want you to always be picturing what the molecules are doing, so that molecular terminology. And then we're going to talk about, well, if you have different temperature in different areas, if we have different pressure or numbers of moles of gas, where is the gas going to move from and to? And then that basically is going to allow us to then proceed into predicting the direction of gas flow in respiration or ventilation, and we're going to use rationale from gas laws. So one of the things we're going to get into is our weather patterns, and these weather patterns are something that you guys should be able to explain. when we get to that point in class on Thursday. But how cool is this?
Can't see the screen well. I would get closer to a TV. You should be able to see stuff.
Anybody see what's going on? So what's it showing? Alex, what's being shown on the screen?
I don't see anything.
Move closer.
One solid circle. Color one.
So none of the colors, blue and green, don't show up in your vision?
I see blue and then I see grayish within the blue.
Do you see movement anywhere? Sorry. Ryan. Sorry, Alex.
See like currents.
Currents of what? Alright, so first glance you want to say it's water. Why is it not water? So they're moving over land, right? So this is our currents as we can see, our wind currents. And these patterns are something that you guys should be able to describe, at least to a simpler level, in terms of gases. Where gases are, where they're likely to go, and how their orientation to the sun affects where they're moving. So let's go through a couple quicker questions. Bringing some physics in. All right, the pressure of a gas is measured by what, Megan? The molecules colliding with each other. What does most of class say? We don't know. Where's your pressure sensor? Is it measuring the collisions between the molecules? What's it measuring, Thomas? It's the molecules colliding with the side of the container where your pressure sensor is. So your pressure sensor is in there. It feels the molecules colliding with it, and based on how fast and how heavy those molecules are, your pressure sensor changes the amount of pressure. So at 27 degrees, we're going to be looking at a molecular view here of a gas. So then the next question is, when we raise the temperature, what happens to the pressure in the system? And how do we explain that on a molecular level? What about that equation? Pressure equals force over area. Demetrius?
I said pressure will increase because measure the amount of pressure on the container. If they're moving constantly, there's more pressure on the container.
Why is there more pressure on the container when they're moving?
Because it's like, well, I'd say like, because they're constantly like moving, they're constantly banging against the container at a faster pace, so there's more pressure.
Great, so it's the speed, right? So the pressure is a measurement of how much force in a given area. So if we increase their speed, the temperature, as you guys were saying earlier, I think Solomon was saying that, right? Which is increasing, the area that we're measuring or the force of each molecule that collides? Force goes up because they weigh the same, but now they have more speed. Means that the pressure we measure goes up. What if we then were to expand the volume of that container? Same temperature, keeping it 35 degrees Celsius. What's going to happen to the pressure if we expand the volume that they're in? And I want you to describe at a molecular level what's going to happen. Talk to your group. Make sure you can explain it on a molecular level. What's changing? All right, everyone clicked in? Sabrina, what were your thoughts on this?
If the volume increases, then there's more area for the molecules to go, which makes the force that it hits the container less powerful. So
Less.
the pressure will decrease.
Okay, so are they going to be hitting the side of the container with less force? Not necessarily. Claudia, what are your thoughts?
You're saying that it would just take longer for like the molecule itself to hit the side of the container.
So it has a longer distance to go before it collides with the side of the container again. So what's the one factor we didn't talk about in that equation? P equals F over A. So you just said, if we increase the volume, what happens to the pressure? It'll go down because? And we're measuring how they hit the side, time. So it's how many molecules hit with what force over a given amount of time. So the time plays a role. If you have more volume, they're going to take longer to collide, and hence you're going to measure a lower pressure. That's bizarre. There we go. Sorry. Clicker didn't show up. Okay, and so, has anyone seen these cool balloons? I just saw this on TV the other day. I need to bring this in. These balloons that are fish. Has anyone seen this? It is so cool.
Oh, like it'll fly around.
Yeah.
Like a shark. I've seen that.
It's a shark, and there's a goldfish, and there's a dolphin, or these other ones. And they're these balloons that have a tail on them, and they have fins on the side, and they have a little motor that propels them forward. So these balloons will float, and they're perfectly balanced, and then they can go up and down. Why is this so cool? Why do I love this right now? What is the connection? What's the connection?
Might be the pressure affecting how it floats.
Okay, so the pressure absolutely affects how it floats. So we always think about fish floating and swimming in what kind of a medium? Water. Why? Okay, so what's the relative density of a fish compared to water? It's got to be about the same, or else if it's less dense, they'd float up. If it's too dense, they would drop down. So what's so cool about this balloon? It's the same density as air. So you can think about that. We think about this as very different from a solution of water, but in a lot of ways, there's some similarities. So you have a fish literally swimming through the air because it is the same density. There's particles all around it. There's particles inside of it, but it's the same density, and so it ends up being buoyant. So cool. So this is. Go ahead. I don't know. It's got to be helium mixture with air, because if it's too much helium, it'd go up. If it's too much air, it'd go down, because it has to carry the weight of the balloon mechanism and stuff too. Or maybe you fill it all with helium and the actual mechanics weight enough to weigh it down. Okay, so the reason I think this is so cool is because I never thought about us, the air that we breathe in. Like, where's the pressure come from? Why is this atmospheric pressure? Where is zero pressure? Anyone think about this? Space is what?
Zero pressure.
Space is zero pressure. We have pressure here. So where does that pressure come from? Gravity and what? Michelle?
Gravity and most of the atmosphere behind space. Like the molecules of the gases have mass. We don't think about that here.
So we don't think about the mass that molecules have, right? But if you think about it, if you're at the bottom of a swimming pool, your ears feel more pressure. Why? There's more water above you. Gravity pulls a lot harder on that because it's more dense, so you feel it a lot more, right? 10 feet down the pool, you feel it in your ears. Same idea is here. We have the atmosphere all above us, all the way top of the atmosphere, and all those molecules are being pulled down by gravity, and that's why we feel more pressure here than higher up in the mountains. What?
I would say, is that why whenever you go to like mountains and stuff, your ears feel different?
So when we go up in an airplane, how much pressure is there in the airplane when we're up at 30,000 feet versus down here? Less, right? There's less molecules colliding with our eardrums, less. So the pressure that's inside of our eardrums needs to equalize. And so there's more pressure on one side than the other, and we feel that difference. This is a diagram that shows if we're up on Mount Everest, literally 30%, 35% of the pressure that we feel down here. 35%. So why is it harder to breathe up on the top of Mount Everest than it is down here? Talk amongst your group. Why is it more difficult to breathe here than it is? We should help because colder means more dense.
No, yeah.
So McKenna, what are your thoughts? Why is it more difficult to breathe at the top of Everest than it is here?
They said there was less oxygen and less particles moving around.
Okay, so is it that the air is composed of less fraction of oxygen?
Can you repeat the question?
So the question was, it's more difficult to breathe at the top of Everest. Is that because there's less total air or less of the air is oxygen? What are your thoughts, Sarah? Here?
There's less pressure at that height, so it's harder for the diaphragm to pull down and pull in that oxygen.
Okay, so it's more difficult to pull in, I would say, air in general. Or when we do pull it in, we get less. Morgan?
So we were talking about how pressure is related to like molecules and like the speed at which they like, hit, the force at which they hit, and the frequency. So if it's like less pressure, then it wouldn't be like the same for like the amount that a particle hits like a particular area. So like for oxygen, for example, there's not as much. If the pressure is lower, then it's like directly related to like the speed or like the amount that's hitting it.
So the assumption that I'm kind of asking you guys to make is that, well, for all we know, that air is the same no matter where you sample it in the atmosphere or stratosphere. That's not completely true, okay? There's the ozone layer. The ozone is much more concentrated up high in the stratosphere, right? But for the most part, the relative amount of the partial pressure of oxygen versus CO2 versus nitrogen is the same at the elevations that we're talking about here. So what's the big difference? It's not the partial pressure, it's, Brianna?
Is it because like the gravitational force pushing at higher elevations isn't pushing on as like small of a volume? So like on the thing that you just showed that had like the box coming down to the earth, it almost looks like it's getting smaller as it's coming to.
Well, careful. So we're saying that the area is the same, but how much mass is there above this point versus above this point?
There's less mass higher up than there is closer to the ground.
So that means that forces those particles less close together. And the closer we get to Earth, the lower down we get, the more gravity squishes those together. So we take one breath here. How many breaths is that equivalent to up at the top of Everest? Three breaths. So the number of particles that our lungs have access to changes drastically based on where we are elevation-wise. Yeah?
What do you mean when we talk about partial pressure?
Great. So partial pressure, we kind of mentioned it last class. We talked about CO2 in the atmosphere. Does anyone want to define partial pressure in these contexts? Don?
So is it that you have a total pressure for, if you added up all of the molecules in air, that they all have to be equal to the pressure of nitrogen, pressure of oxygen, pressure of carbon dioxide, or carbon dioxide?
Okay, so I'm going to add to what you said. No matter what the total pressure is, that there's parts that make up that. And if there's a total of 1 atmosphere, then the partial pressure of nitrogen is 0.78 atmospheres. So Dalton's law of partial pressure says that the sum of all the individual pressures, or how frequently they collide, all of those add up to the total pressure that we observe. And that's why we observe it, because all the different molecules that are there. So the partial pressure of any gas depends on what percentage it is and what the total pressure is. So the relative percentage should be about the same in all these different elevations, but the total pressure is less, so the partial pressure will be less as well. Done?
Sorry. If we have R as the constant, and you're saying that that's every gas, why is the partial pressure of nitrogen and air less than oxygen? Shouldn't they all be the same if they all have the same constant?
Okay, so that's a really good point. So there's 2 points. One, the gas constant. Is that really constant? If we're up at a higher elevation or lower elevation, or we're looking at different temperatures, should that gas constant be the same?
Constant's the same, but you're comparing it
Constant.
to say up 0 degrees Celsius and at 118.
Right. So the gas constant, in theory, tells us a scalability between all the different things at standard temperature and pressure. As one goes up, the other should come down, though. So that gas constant stays constant. The other side of your question was, well, with 1 mole at standard temperature and pressure, everything occupies the same space. But that doesn't say how much is actually here. It just says if I was to isolate nitrogen gas, it would occupy 22.4 liters for 1 mole. But that's not all that's here. There's a big mixture. So we can say, the cool thing about that is, if I take 22.4 liters of air at 0 degrees, what's the total number of molecules I have in that? 6.022 times 10 to the 23rd. It's a mixture. It's all different molecules, right? But they all add up with their partial pressure to that total. Other really cool thing, and I love these visuals that really bring home something I never thought about before. Have you guys seen a manometer? Does anyone watch the Muppets? Phenomenal. Okay, so this is a manometer. Manometers do this really, really, really cool thing where you take a tube, a glass tube, you pull every single gas molecule out, completely empty, and you put your thumb over it. Not really, because it would blow up your thumb. You put it into mercury, and then you let go. Mercury rises up inside this tube. Why? Why does mercury go up inside the tube that has a lack of molecules inside of it? So think about it for a sec. Talk to your group. Why does mercury go up this tube?
Since pressure's exerted down, like needs somewhere to go. Water will move
Tatiana, why does the mercury go up inside of that evacuated tube? What's that? Any ideas? Brooke, what are your thoughts?
We thought it could have been density, but I'm not sure.
The mercury is really, really, really dense. So it's not likely to go up there, but it does. So what is it that's driving it? James?
You're thinking of pressure, so the air pressure going down on the mercury would be higher than no pressure in the vacuum tube, so it would push it from high pressure to low pressure.
So what's crazy about these things is it's literally not being pulled, it's being pushed up into the tube. That column of air that's above the exposed mercury is pushing down, and that the only place mercury has to go is where there's nothing pushing back on it, which is inside that glass tube. Just a different way about thinking about pressure, right? The difference between two areas of pressure, which direction are things going to flow? That's what we're going to be getting into. So, Ms. Terrell had an announcement or a comment?
Just really quickly, going back to the example Dr. Wheeler had about Mount Everest and the pressures that you have at different elevations, it would be really, really important to think about that in context of the ability to take on oxygen into hemoglobin and for that oxygen's ability to come across the barrier and dissolve into blood. So keep that in mind as we're going forward. We're going to get into that in a few weeks with biology.
Question, Chase?
Yeah, on the last slide for that, if it was a true vacuum, would mercury go all the way up to the top? Because it would have to equalize the pressure inside and out, and
So
then there'd
what's-
be no air particles whatsoever. So
Well, what's keeping the mercury from going all the way up? Why doesn't it just slam up there if there's any pressure outside?
because I was thinking like the air is trying, when the mercury's pushing up, is trying to get that air to the same pressure outside. So it'd be like trying
Yep,
to
but
get
there's no pressure here, so no matter what, we're not going to get to
Yeah.
the same pressure. So what is it that's keeping that mercury from going all the way up? So it does have density that's
Gravity.
higher. What's that?
gravity.
Gravity.
Okay.
Gravity's pulling down on the mercury, air is pushing down on the mercury, that those two are competing against each other, and so that determines how high this column is able to get before gravity wins out, and it stabilizes the equilibrium between the two. Alright, so let's watch a cool little video and see if you guys are smarter than Destin's child. Has anyone watched Smarter Every Day? And I think it might have, damn it, reloaded. So it's going to be 3 seconds until we can watch this.
Hey, it's me, Destin. Welcome back to Smarter Every Day. So today we're in the rocket van, and I've got two little science helpers here, right? Are you wearing your seatbelts? Okay, we're going to do something pretty interesting. Check this out. I've got a pendulum suspended from the top of our family van, and we're just going to drive forward. We're going to accelerate. So if we're going that way, which direction do you think this pendulum should go? What do you think? 3, 2, 1, go.
Yes.
Which way is it going?
My way.
That's right. It's because I'm accelerating, right? Does that make sense to you guys?
Yes, sir.
Okay, very good. I was hoping it would make sense. So we're going to change it up just a little bit. Okay, so now what I'm going to do is I'm going to replace this pendulum with a balloon. We should see the same thing, right? Let me cut this off. So what we're going to do is we're going to accelerate that way. So we have the mass of the balloon and the acceleration, so that should net in a force, and we'll have to react with this string, right? You guys ready?
So what's going to happen? You can talk to your neighbor if you want. All right, you guys want to see what happens? Ready?
Yes, sir.
3, 2, 1, go. Wait a second. What just happened? Oh, what happens when I stop? The balloon goes backwards when I stop. What's happening?
What's going on? Talk amongst your group. Try to figure out what just happened and why. Think about the molecular explanation of this. Alright, so who wants to share the thoughts?
Like the center of gravity of that.
Morgan, what are your thoughts?
So with the pendulum, it was denser in the air, so when it moved forward, it moved back, but the balloon, since it's floating, it would float away. It's less dense than the air, so when it moves forward, the air moves back and pushes that forward because that was.
It's still the same.
3, 2, 1, go. There it is. It's coming right at me. Why is it doing that? Do you want to know?
Yeah.
I brought something to show you. Remember I told you I was going to bring this jar earlier? Remember that? So it's like this. Imagine this entire van is just like this jar. And all the air inside this van is just like the water in the jar. Does that make sense? So let's imagine that the balloon is this bubble on top. Because the helium in the balloon is lighter than air, right? So that causes it to do what?
Go up.
Go up, that's right. So if I've got this air that's just like it, what happens if I move the jar that way? All that water sloshes to the back. And when that water sloshes back this way, which direction does the bubble go? You see that? So the air bubble moves in the direction of acceleration. Does that make sense? I know you're 5, but I think you can get this. Okay, so I've got my seatbelt on. If I drive forward real fast right now, which direction is the balloon going to go?
Forward.
Why will it go forward?
Because all the air is splashing back.
That's right. Very good. Watch this. Look at that. See that? So you know what that means, don't you? That means you have more air to breathe than Daddy does when I'm going fast. Did you realize that?
No.
Yeah, that means when I go fast, that means more air sloshes back there to you, and you have more oxygen to breathe. Doesn't it feel good back there? Okay. So
Okay, so one of the things we said is that no matter what the gas is, 1 mole will still occupy the same volume. So then how do we say gases have different density? How do we fit those two things together? What particles?
They have more, the denser nuclei.
So if we have a mole of water versus a mole of hydrogen, how many particles are they both? It's the same number of particles, right? So they'll occupy the same volume space. Is one heavier than the other? So that means their relative densities is going to be different, which is why helium floats and the air sinks. So we're trying to get you guys to really have this molecular view of gases and to be able to make predictions based off of that. So let's do our last little bit here, which is about ventilation. Which one of these two images, if you can't see it, move closer. Which one of these two images shows Skeletor exhaling? What was that?
You left the answer.
It's up. Oh, there. All right, so look at the diagram and try to answer based off of that. And why? I want you guys to explain why that one would be exhaling. What's happening on the molecular level when in that particular diagram? Is everyone clicked in? Okay, so even though it's written at the bottom, we still got some people that didn't answer it. Okay, so B is him exhaling. Why? Molecularly, what's happening in the one on the right? Talk amongst your group. Try to figure out what's happening on the one on the right that makes Skeletor, us know that Skeletor is exhaling. Okay, that's not why it's going out, right? So then why is the air leaving? You guys are good.
Well, I was saying in anatomy, I learned that when you inhale, your vaginal goes down.
So let's think about the molecular version of that. So if his chest is contracted, his diaphragm relaxes, then that means what about the air in the lungs? So you're giving it less space, so what happens to the collisions? More frequent collisions, right? Okay, so can I hear? Dan, can I hear from you? What are your thoughts? Like, how do we know that that one on the right, how can we explain from a molecular viewpoint that that's him exhaling?
Honestly, I don't know how to explain it. I saw the writing.
Chelsea? Okay, so something about the density is probably changing. Does anyone want to add to that? Brianna?
When your diaphragm relaxes, it doesn't it moves up kind of, and because it's moving up, your lungs don't have as much space to be expanded anymore, so they contract, which is why the chest contracts and then the air comes out.
Okay, so why does the air come out? That's the question.
Because there's less room for it in your lungs.
Okay, so there's less room. We decrease the volume, so what happens to the molecules? They become more pressurized, which on a molecular level means?
They start moving faster.
Val?
They collide into your lungs.
They collide more or less frequently? More frequently, so the pressure goes up. Okay, so we contract our lungs, the pressure goes up. So then why do we exhale? Why does air leave our lungs then? The biggest part of this that people forget about is it doesn't matter how much pressure is in our lungs, right? It's the relative pressure between our lungs and outside. So when we're breathing, is there any point in time at which the pressure inside our lungs equals the pressure outside of our lungs?
When we're dead. Maybe halfway.
What do you mean halfway?
Like when your chest is not all, it's like when you not all the way expanded or.
So someone show me what it looks like when our pressure inside and outside of our lungs are equal. What? There's probably a lot more pressure outside from the water once you go in, but maybe, I don't know. So when we're holding our breath and our mouth is open. The peak of our breath and the bottom of our breath, that's the time in which no air is going in or out because the pressure on the two sides is equal. So if he closes his mouth, and then he tries to inhale, then what can we say about the pressure in his lungs compared to atmospheric pressure? Closing his mouth and his nose, and he's a skeleton, but he can still close them all. So what can we say about the pressure in his lungs compared to outside if he's trying to inhale but no air is coming in? Everyone clicked in? Really? If we're trying to inhale, do we have a greater or less pressure in our lungs than outside? Less. Air goes from an area of higher density or higher pressure to lower. It's always going to equilibrate. And if we give it time, that'll happen. All right, we'll catch up. We'll start on weather patterns on Thursday, and those weather patterns will help solidify the concepts we've talked about here. So it's not new material, but it'll be building on it.